We'll just wait for a few minutes and then start. In the meantime, if you guys have any questions, feel free to ask me. Okay, we'll start. Just recap whatever we covered last session. Okay. So first of all, the friend function. So in a given class, let's say I have some public function, which is the display here, and I do not provide any definition for it. Okay. So what one can then do is provide the definition outside the class, and the friend function now uses the definition of outside the class. Okay. The reason to use friend particularly is that your function now has access to even the private member variables. Okay. Normally in inheritance, like we saw later on, uh, inheritance does not have access to the private members. Okay, even for the base class. But if you make the given class, which could be the base class later on, that class has some private member data that you can access using the friend functions. Okay, that is sort of the essential idea here. So we declare the data member, we declare the constructor for the class, my class. Okay, so it takes the data member, some underscore data, sets it to the data member and says that it's cost constructed. Okay, so that's the print line, right? And then we have the function display. To call the display outside, okay, has the body that it just prints A. Like for that object A, it prints the data. Ideally, data is, while it's a private member, it should not have access to it. But because it's a friend function, it has access to it. Okay, right. Then yeah, then we saw about inheritance, where listen, there's a base class, which has some private members, some public member, and some protected member. Okay. When we derive a class from this base class itself, the derived class itself can have some uh, private members, right? So if nothing is mentioned, by default, that is private. Okay. For public and others, you have to explicitly mention that it's this region of your code is public and this is protected. Okay. Um, so we declare private member variables. Then we have public member variables and the protected one. Okay. Here in this example, like using this void function, just func. I don't call this function actually, if you see, but for it to actually compile, it essentially accesses this operators, as in this the object of this derived class, its own whatever variable it has access to. As in, if the data 1D I'm calling with respect to the object of this class, the derived class, not with of the not that of the base class. Okay. While there is an inheritance, there's a limit to which variables you can access. Right. So 1D, while it's a private member of the derived class, you can access it within the class. That is okay. Even 2D is also fine because it's public, again, accessible within the class. 3D, protected, yes, which when something is protected, its derived classes have access to it. So its derived classes will have access to it. But if you take example of just private members, then that's okay for the same class, right? I meant the protected members. Okay. So this is accessible. We don't do anything with it currently, but that's okay. The idea is that which is the level of access where you get. Okay. So which data member can be accessed where? That's the only idea here. Derived classes cannot access data 1B here, which is the private member of the base class. So we don't have access to them. Okay. Next, we have the data 2B, which is public. So while it also gets inherited, you can access it. And then data 3B. Okay. So that is the protected member, which also again has access to the data. Okay. Now, protected especially has access because this is again protected. So when you have inheritance, it has access to it. Okay. right? Then you have the base member. So yeah, when there's another way you can access the same data 1B, right? But not the inherited one, but whichever is what are you getting from the base class itself. Okay, you can try accessing the base class variables themselves using this namespace. Okay, you can access the public one, not again the private one you cannot access. You can access the public one. Okay, protected again you can access because it's accessible, right? It's a derived class, it can access this data. Remember, the difference is that when you access the data 3B, this is a copy of the derived, this is a copy of the base class, which derived class owns. So hence this operator. Okay. But when you use the namespace of base, you're accessing the data, which is owned by the base itself. Okay. Right. And it has a protected data member, which anyway, if we make a derived class out of this derived class, that will be useful in that case. But otherwise, yeah, the derived class itself can have access to it. When you make the base class, the objects of the classes base and derived, the only thing to remember is that because it's outside the base, outside the classes, only public member variables are available. So data 2B and data 2D only are available. That's what you see here. Okay. Now the only difference is that which are you accessing where? That's all. Accessing B is data 2B, B is data 2D, and D is data 2B. Okay. Yeah. Right. Moving on. So next we see another form of inheritance where we are not just dealing with variables, but let's deal with some functions. Simple enough. You have, let's say, a base class, right, which has the function definitions for f and g, and I make a derived class. So being public or not, uh, by the virtue of being a derived class, it inherits all these functions f and g, and because they're public, you can call them through b and d also, both. Okay. So we make an object of b, small b, object of base, small b, and object of derived, small d. So b dot f you can call because again it owns these functions f and g, and these are public, so you can call them, and it prints whatever relevant values it has to. Very similar to that, you can also print d, like call f and g from d because it's inherited from the base class base. Okay. Next, yeah, before this, I guess. Oh yeah, before that, function overloading. So let's say I have a function func. Okay, it has some body. Let's say it prints body 1, body 2, body 3, body 4. So these are all different functions. But the commonality is that each of this function, okay, is different in the sense that while the signature is same, so as in whatever is the return output, it's all void. The name of the function is same. The only thing you can differ in that function to make it different than the other is that whatever input parameters it takes. Okay, here it does not take anything. It takes an integer, float, and double. Okay, because of this very reason that you're changing your data types as inputs, your body of your function changes. Okay, and because this changes, the one might actually ask why you can do this. The reason is that they are treated as separate functions. In a way, you can think that way. So while the function name itself will seem same when you're calling the function, okay, the difference is that because the input parameter changes, you can actually write different definitions, okay, accordingly. So this feature of C++ is called function overloading. Okay, you overload the function, same name, with different data types. Okay, using the very same idea, let's look at the same thing in C++ object-oriented programming. So we have a base class. As before, we have f and g, which output certain values. Okay. Next, we get a derived class also. We make a derived class from this base. So it would inherit f and g too, right? But furthermore, what we did here is we made fgh already And again, those also are return type void as here. Excuse me. So the return type here is a void, but what we're going to do is differ only in the input types. If you look at G, let's not look at F first. So let's look at G. G has integer I and float I. So because these are different input parameters, so the one can treat them as being overloaded. It inherits the G from which takes integer from base. Okay. Now derived class has two functions with the name G. One which takes its own thing, which takes float, another which takes integer. And accordingly, it can have two different definitions. That is absolutely allowed. Okay. But if you look at F, it takes integer I, and already there was an integer I. So the base class already provided definition, but derived class sort of has its own. Okay, so which actually gets used. So in this case, the one by the derived class wins over. Okay, so this is called function overriding. You're overriding the definition you're inheriting. Okay, by the definition you're currently providing. Okay, so if you call f from b from the base class b's object, this will get called. When you call f from derived class, like we do here, this definition will get called. Okay. In G, depending on what is the input parameter, both one of them will get called if you're calling from derived class. Okay. And if you're calling from calling H, this is just a new definition. That's absolutely okay. But H is not available in base. Okay. So if you try to call B dot H, that is incorrect. Okay. I did not add something else. Let's say I so double, right? So 10.5 H. Not allowed. Okay. Okay. Because it is part of the derived class, not of the base class. Okay. Similarly, if you try to call base class with inputs as floats or doubles, that is not possible because it only has definition for integers. Okay. All right. Any questions? Okay, moving on. So today we'll learn about typecasting. So as usual, let's include the IO stream file. Then write the main function. Okay. Yeah. Can you tell me what are the basic data types that oh, okay, there's a the questions first void function with underscore, is it not getting anything? Okay, I think I closed it. Do you mean this one? Oh, okay. Can you repeat your question? Inside any of this class or just a plain old function, like let's say a free function like this? You can. Yeah, that's absolutely allowed. Yes. Yeah, you can. You can write it this way. Yeah. You can actually put it outside the classes. Okay. As in, then you can actually call the function like this. Okay. And it has some definition. Okay. Okay. Some the body. Okay. This is absolutely allowed. Yeah. Then you have to end here a function with a semicolon. That's it. You can put it outside any like outside such that it's not there in any of these classes. You can also do it this way. You can put it inside the classes itself. That's also open. But then you have to call this function from the using the object of the class. Yeah. Oh, that's what. So having a parameter is a kind of function. Having no parameter is also a kind of function. There are three things to determining what exact function to be called. Okay. One is the return data type, name of the function, and whatever input it takes. These are the only three things. So once these three things match exactly when you are calling to some definition already existing, then that function gets called. Okay. So which one? The F is are asking about F? Just getting rewrite from F and F in base and F in derived. Is that the case? Are you asking about F and F here? Okay, I'll just repeat it. The reason you have, let's say, F already here and another one here, there's no particular reason. So what the concept here is that if at all you do it, okay, we might actually find some use case for this. Sure. If at all you encounter such a situation where you are giving the same return type, the name and the input parameter, and in your derived class also has the same thing, okay, and they have different body, right? So essentially they're different definitions if you think about it. Then what happens is function overriding takes place, okay, where when you call the derived class as F, this function gets called, okay, not this one, right? In the case with G, it just so happens that these two definitions can coexist because they have different input parameters. They coexist in the derived class, not in the base class. You cannot call G with a float in base class because it does not exist there. Okay. I hope that is clear. Okay. All right. So moving on. And anybody tell me what are the inbuilt data types that we usually encounter? Just name some. Yeah, that's correct. We have integer. So let's say there is an integer I. I'll define it to be 8. Another one was float. Okay. So float f, let's say it's 9.8. And another one was double. Yes, double. If d equals to 3.14. Let's say. Yes, character also correct. Boolean, bool. So these are some of the inbuilt data types. Like you can think of them like very fundamental, and those are something we use to define our variables, because C++ being a strongly uh, typed language, when you say something to be integer or float or character, it establishes that the data type or how much space it or your variable should take. Okay. Not just that, how should uh, your computer OS interpret that data? If it's 32-bit integer, then it will use a certain way of calculating what that 32 bits actually represent in numbers, like what integer it corresponds to. And there's a rule for if that 32-bit floating point number corresponds to what uh, real number. Okay, that's essentially the idea there. Now, these are straightforward. So I'll just let's say print this. So let's say I is this. Okay. F G. Oh, sorry. D. In general, this is also important. This is in general 32 bits. Again, it depends on the compiler and your architecture. This need not always be 32 bits. Okay. If you want exactly to be a certain size, you can use some inbuilt data types. There are certain ways you can access them also. Like you use int underscore 32, and so on and so forth. Okay. But usually if you use the data types plain as such, where you're putting integer float, these are usually 32 bits and the double is 64 bits. Okay. Essentially, it's like float, but you have more precision. You can access 64-bit integer also. You just add the word long. So long int I or long int, let's say j. Okay. Now, let's say I do this. So what I'm doing is I'm converting, okay, or think of it this way. I'm having integer I, okay, which is some 32-bit number. I'm storing that in a double, right? So it's like converting an integer to a real number. Nothing wrong with that. It can be done. Okay. There are more nuances to it. Let's look at it one by one. The first thing to notice here is that it's an implicit conversion. Okay. I'm not specifying that you have to convert from this type to this type. It's sort of inferred here, and this will work. Okay. And let's say I print D now. It'll look something like it'll print something, right? So let's just look at that. Okay. So the first one prints them correctly as in expected also. 8, 9.8, 3.14. That's what we get. The second one, when we write 8 itself to double, okay, so the variable d, 3.14 gets overwritten, and now we have 8. Okay. I did not have to choose or tell the compiler that I'm trying to convert an integer to a double. it implicitly did it. Okay. Then you do not have to actually specify something, okay, which is the would have been the explicit way. The other opposite is the implicit way. Okay. Now, let's say I do the same thing, but this time I write it this way. Okay. In this case, I'm explicitly casting from integer to double. Okay. After this, I can again print D, right? And let's look at the answer. I actually did it already, so doing it twice doesn't make sense. Let's skip this. Let comment this out so that we actually see the result of how explicit also does. It does exactly the same thing. Okay, what we saw in the implicit cast. It just so happens that you're explicitly saying that you want to convert I to a double, like you're essentially typecasting. Okay, so this is what typecasting is. You're essentially typecasting I to a double and then storing it. Okay. The end result is the same here and here. The only difference is that here it is done implicitly. Okay. While the compiler just sees it and does it for you. Okay. But if you want to do something explicitly, that is also possible. Okay. Right. Next, we can do it the opposite way. Let's say we do this. Okay. We were converting an integer to a double, right? We can also try to convert a double to integer. Now here, because of the representation, the numbers that double can represent, okay, it can actually also represent a lot of integers. Okay. Just so happens that numbers like 8 are too small here. Okay. So it actually represents them exactly. Okay. Remember, here you have to be very thorough or clear about representation of numbers on architectures. So float and double follow a certain representation rule, and integers themselves follow a different rule. Okay. The idea sort of extends from 32 bits to 64 bits and whatever. Okay. But whatever the rule is, it is different for real and integers. Okay. Now, when converting integer to double, it has enough bits, okay, to exactly represent this number 8, because it is not too big actually. Okay. You can go through the representation to understand this more. Struct. Casting can be done on struct. Technically, yes. Oh, yeah, you can. Yes. So we'll actually come to that. Yeah. So I'm just covering the inbuilt data types first. Then we'll come to the custom data types, or more specifically objects. Okay. And you can think of structs like objects also. While structs are available from C language, objects came in C++, but you can also typecast objects, or similarly, you can typecast structs also. Yeah. It just depends, like, what you're trying to achieve. Right? That's the idea. Okay. Now, looking at here, because I have a double, which is 3.14, okay, I'm trying to cast it to I, right? Let's look. So this will actually give you oh, it actually did it, right? Oh, yeah, I should print it actually. Usually they don't allow it. Well, going with explicit casting is better here in this case, but then I guess depends on the compiler. All right. Oh, I should actually comment this up. Yeah, sorry for that. So it just so inferred that because you have a real number which has a integer part and a fractional part, I'll just drop off the fractional part, and whatever integer part is there, I'll just represent it. Just so happens that 3 is also small enough. to be easily represented in 32 bits. Okay, right? It did do this implicitly here, right? It's usually advisable actually to do it explicitly. Reason being, you are converting because you're dropping off fractional parts. Essentially, you are losing some more information. Yeah. So that's what, because I is an integer, it cannot, it does not have any idea about uh, decimal parts or fractional parts. Okay. It can only represent integers. So when you convert your real numbers to integers, it drops off those parts. Okay. So this is also explicit casting. Okay. Yeah, that's the thing. So some of the I think old versions of compilers, they don't actually allow this. They actually throw a error or warning, sometimes warning, but error sometimes also, that if you want to do it, you should do it explicitly. Reason being, you are actually doing a demotion. You're not promoting your integer to become real, like in this case, which is sort of straightforward and allowed. Okay. And numbers, for small numbers, you don't actually lose anything. And when your integers are too big, okay, then only it becomes an issue. What I mean to say is, if you see the representation to what values your real numbers can represent and to what values your integers can represent, okay, just so happens that those integers can be represented exactly. And I'm just talking about double, okay, integer and double. Here it goes, I think, like yeah, whatever values I forget, but till those, that range of integers, you can represent them exactly in double. Okay, so there is no issue there if you convert from one to the other, like integer to double. But when you convert any double to integer, there is no way it can represent the number exactly, because if it has fractional parts, integer cannot represent those bits. Okay, you're converting from one rule. So again, I really highly recommend learning about floating point representations of both 32-bit and 64-bit integers, representations in both 32 bits and 64 bits, and also the 2's complement representation, which is generally used for integers, both 32 bits and 64 bits. Okay, they are pretty much the same idea, but extended to other, like these higher bits. Okay, but remember, whatever rule float or double uses, it is completely different from whatever rule integer uses. Okay, now to give more idea or context, there is sort of a hierarchy. So when I say integer and double, okay, so double will have the most information, right? And you can exactly represent uh, integers which are 32 bits in this. Okay, now how does this? So that is sort of like here we are promoting a integer to a double. So there is sort of no loss of data. So this is called promotion. When you actually demote it, you're chopping off or truncating the data, then it is a demotion. And this is the hierarchy in C++, I guess C also. Full character, short int, then you have int, unsigned int, long, unsigned long int. I'll just call it unsigned long, long. float, double, long double. Okay. Another thing, so you can use there is a set precision using here you set this using standard precision. So when you print values here, okay, you can actually print a lot more values. So by default, there's a trunk. It will only print to certain range. And let's say you have a very large number where I mean, when I say large number, I meant like large decimals. Okay, like let's say 5, 6, 7, like 10, 15, or let's say something like that. Depending on how much you can actually represent, okay, in your 32-bit or 64-bit representation, till a certain number, it is useful. It's actually exactly represented. The others are anyway, no, bits will be garbage. But to exactly print those bits which are actually exactly represented, like let's say all of them, you can use standard precision along with standard cout. Okay, something to try for. All right. Any questions? All right. So moving on. We have main function. There is, let's say, 3. Okay. And I have another integer, but this time a pointer, p, which points to, let's say, I itself. So I is a value which has 3, and a p is a pointer pointing to I. This is okay. So again, defining integer, but this time array of it. So let's say a is 10. Okay, so this is a C style static array, and let's define double p 7.5 double pointer to, which is taking address of d. And finally, let's make a void pointer. A void data type, void pointer R. Okay. Probably, yeah. Okay, that's okay. Now, let's try to write equals to p. Previously, we did convert an integer to a double, right? We promoted an integer to become a double, and implicitly that was allowed. Okay, there's no problem or issue there. But what if we try to convert a pointer to another data type? So exactly the same idea, double to integer, but this time a double pointer. Okay. Sorry, integer to a double. I'm sorry about that. We promoted an integer to a double. Okay. But what if we promote an integer pointer p to double q? Okay. Let's see. Error. Okay. So the reason for this is while conversion from a number to a number, it knows what to follow. Okay. And that is implicitly okay. But when you're converting, like writing addresses here, the difference is that while the actual address size is the same here, so the size what Q holds and the size that P holds is exactly the same. It's a 64-bit integer. Okay, unsigned integer, which is the address of in the memory. Now both of these values have the same exact space, but the pointer they're pointing to are different. So one is a double pointer and this is integer pointer. Okay, so C++ does not allow you to rewrite pointers implicitly like this, like through um, implicit casting. Very similar to that. If you try to do this also, it should throw an error. Yeah, both of them. That's good. Okay. So not cast them, sorry, you cannot cast them the pointers, okay, implicitly. That's something to remember. But does that mean that we cannot cast them at all? No, you just have to cast them explicitly. Okay. So what we can then do is let's just print it to check what values currently are present. So it will be a pointer q, a pointer q. Okay. Then we have, let's say, q e, right? So like I said before, you have to implicitly cast. You cannot implicitly cast it. So we explicitly cast it. So remember, q is double pointer. So we'll be converting p to a double pointer. Okay. Now this is the C style syntax of convert typecasting. We will also look at the C++ way of doing the same thing, which are more specific in what exact typecasting are they actually doing. Okay. Here we are saying that we take a pointer p, okay, whatever address it is pointing to now becomes double. Okay. What that means is, let's say there was an arrangement of bits at so p originally had some address, right? And that address was pointing to something in memory. So that, let's say the address was this, I mean like 0x 5671, something like that. Okay. And the actual this is the address that it contains, and this actual address starts with certain bits. Let's say this, it was this 0 1 1 0 something 0, something like this. Okay. Interpreting, and this will be 32 bits. I'm not writing it completely, but just for example, just think that this is 32 bits. In the rule of 2's complement, interpreting this 32 bits, okay, somehow gives 3. Okay, that is the idea. So when you interpret this 32 bits, okay, as an integer, you get 3 as a number. Okay, but what does this casting did do? What it did is, it took the address, which was this guy, okay, it treated it as a double pointer, okay, stored it in Q. So now Q, let's say, had some other address, uh, whatever it was, but now right now it has this address. And because this address has this 32 bits, okay, Q will interpret this 32 bits as a double now. So when these 32 bits are interpreted as a double using the floating point representation rule, they will give you some other number, which is not 3. Very likely not 3. Let's just go with that. Yeah, I'll explain again. So here you have to understand certain like pointers and floating point representation both. So I'll repeat it again. Yeah, I'll repeat it, but if you guys want to revise, definitely revise how pointers work. So we have covered that before. That is one. Second thing is, definitely do look up how representation of numbers work. Okay, both for integers and for real numbers, or like double and float. Okay, I'll repeat again. Uh, okay, let's think that's the better way. Let's not give these examples like this. I'll just print it. Let's go with this. Mm. Oh, my bad. Yeah. What I wanted to print is this actually. Okay. So what I did is, let's take Q first. Okay. So if I print Q itself, it prints the address, whatever it stores, or whatever the Q is pointing to, right? And when you dereference Q, you are interpreting whatever the bits it is pointing to, okay? Right? Okay, as 7.5. Fair enough, right? Because that's what Q is pointing to. Q is pointing to D, where D has 7.5 as the value, right? Okay. But if we do the same thing, but now with P. Let's say P. P. Okay. Now let's print it. What we say is it's a different address. Okay. If you look at P, it's a different address than Q, and whatever value it is pointing to is 3. Okay. Now what I'm telling you is while the value P had Q had the address of 0 6 something something. Okay. Now that will get overwritten with this value. Okay. Furthermore, the P itself had the value 3. Okay. Now 3 itself in binary bits, in 32 bits, has some arrangement. Let's say it is this. It should not be this, but then whatever. Just assume it is this. Okay. It has probably a lot of zeros and then 1 somewhere here. But anyway, nonetheless, it has some representation in 32 bits. These are not 32 bits, but then again, imagine. Where is this number? The number is actually at P, okay, this guy here, which is a starting address. Okay. Next, this number, when interpreted as a 2's complement representation for integers, okay, remember 32 bits are 32 bits and they are zeros and ones. They are zeros and ones and 32 bits for integers, also for floats. Okay, the size is exactly the same. It is 32 bits. The way you interpret those 32 bits is the only difference. If you call it float or you call it integer. Okay, so those 32 bits, which when interpreted in as an integer, give you the number 3. Okay, but now when we give the same address now to Q, okay, right, which is a double, what it will see is it will see the same 32 bits, zeros and ones. Okay, but it will interpret this 32 bits as a floating point number, not as an integer. And what rule does it use to interpret floating point numbers? The floating point standard. Okay, in that standard, let's do this and look at it. In that standard, if I print the same thing again, okay, you see it has the same address as P, right? Q now it used to have a different address. Now it has a say now it has the different, like it used to have some address because it was pointing to D here. Now it is pointing to the integer of P, so that will be I, right? Now that is this address, as you see. P and Q now have the same address. That's what, because we overwrote it. But when you dereference Q now, it won't give you 7.5 anymore. That's obvious. But why should it give? Oh, sorry, is there a question? Yeah. So the thing is, your address is the same, okay, and you have 32 bits. That is some kind of arrangement in your memory. In interpretation of integers, the number is 3. Okay, but when you take the same bit representation but interpret as a floating point number in this floating point standard, okay, you get this number. That's the only difference. Okay, so here you did a typecasting of pointers. Okay, but in the process, you are reinterpreting the same memory location in a different light. You're thinking of in a certain context of P, okay, yeah, in context of P, it is the number 3. In the context of Q, okay, which is now same point is the same address, it is 2.12 into 10 power minus 314. Okay, right?
So can we say that some bits of 3 are representing mantissa and some bits are representing its exponents? That is why the number is changed to 2 point something.
Yes, that's correct. So if you take 3 itself and represent it as a exponent, okay, so this is in bind, yeah, this is maybe this will be easier to type. This is in decimal system, some 32-bit string, okay, some arrangement of 32 bits in integer system gives you 3. The same exact 32-bit arrangement gives you this number in floating point interpretation. Just so happens that the mantissa or the characteristic or whatever we want to call it, all this partitioning and everything, that depends on the actual rule you're using. The rule, when I say, is it the integer rule or the floating point rule? They have their own ways of dealing with it. Nonetheless, at the end of the day, you convert this decimal number to 32-bit bits. You convert 3 into the decimal number into 32 bits. They'll have exactly the same bits. Okay. Right. Very similarly, one can also do this. There's nothing stopping you from going in opposite direction also. Right? Here we explicitly casted from integer to double, and here we're casting from double to integer. Okay. Now let's print the same thing. So yeah, previously this is the address, the number it was pointing to 7.5. P has this address pointing towards 3. The new number address is pointing to this, and when reinterpreted, okay, the same bits are now in integer form, it is a 0. Okay. Again, it really depends on the representation. Okay, whatever rule you are using, and the rule is fixed. We do not change that rule. Okay, as in when I say that, I mean how a 32 bit string or number, whatever you want to think about it, looks as an integer. That rule is fixed. How a 32-bit number or string, whatever, looks as a floating point number, that is also fixed. Okay, that is the standard. You can think in that way also. Okay, any questions? This might actually feel a little confusing at first, but once you get used to it, it will feel natural. The idea is that there are always bits which are represented inside the computer, okay? Be it 32, 64, 8, 16, whatever. Those same bits are interpreted as integers, floating point numbers, or whatever. And there is a rule to convert one from the other. That's it. That's all that's happening. Okay. How does it actually do that conversion from one to another? Is something you can look into. Okay. So to convert pointers from one to another, you have to have explicit casting like this. You cannot do it implicitly. That's what we saw. Except for one case. When you're converting anything to a void. Oh, yeah. Okay. This is absolutely okay. So void, what it does is you're essentially saying whatever may be the address you have, you just put it there. And just forget if it was you were interpreting it as an integer or anything. It's absolutely okay. You're not interpreting as anything now. This by implicitly is not a problem because you're essentially saying, yeah, just forget it. It's okay, right? So this is actually that's why allowed. So here we are putting a address or string of address as in like something like this number, okay, which your P was holding inside R, and Q very similarly whatever it was holding, okay, like something like this here. Oh, I'm sorry. P was this which gets stored in R. Similarly, you can store Q also in R, and this is implicitly allowed because all you're telling to your compiler is that you can interpret you can just store it in a different the same thing in a it just so happens that you don't care about the data type anymore. But the nice thing is because you do a explicit casting, you can store the same thing in a void and cast it to anything you please. Okay, it is possible that what you cast it to might not actually make any sense. It could give you could give you garbage results, but C++ allows you to do that. Okay, so that is allowed. Again, opposite is not allowed. I think you can guess why. Here you are saying, I have a void pointer. Now I want to cast it to integer pointer. Allowed, yes, but not implicitly. So compiler does not like that. Okay, you can do this explicitly though. Okay, as we see, that is the error. Okay, fine. Okay, explicitly though, yeah, that is absolutely okay. So P is integer, so I'll put it integer pointer R. Q is double pointer, okay, and R. So this is allowed. Uh, yeah, all right. Okay. Furthermore, you can also do this explicitly. Nothing stops you in doing it. Being more explicit is actually better because then you are showing the intention that you want it to actually convert. So hence, it is doing it. So yeah, this is also valid. It does it implicitly in this case. We do this explicitly. Okay. I do feel this is better because this makes your intent clear. And yeah, there's nothing to lose actually if your code is uh, more readable and more explicit in what it is actually doing. Okay, right? Yeah. Another thing about pointers. So let me write a loop. Looking back here, so we used I and P and everything, but we did declare A. So let's use that. So usually This is some of the ways you can iterate through a C style array. You use the bracket operator, I, and then just write over it. Okay. There is a second way of doing the same thing where you use pointer arithmetics. Okay. Where A is the starting pointer. So remember, when we declare an integer A of 10, it means there is a block of memory with 10 values, each value being of data type integer. Okay. So it knows the total size, how much it has to allocate, and the starting address is stored at A. Okay. So very much similar to integer pointer P, where P is a pointer, A is also a pointer. Okay. It does a dual serve purpose. It here in this with this syntax, you're telling that I'm going to store 10 values of integers, and the name of that variable will be A. Okay. You can think in this abstract way. In particularly in C and C++, A is the pointer which stores the starting address. All right. Now, if I add any other integer to it, it will shift that starting pointer address by that amount. Okay. Ideally, how much it actually shifts is A plus I times, I mean, if you exactly think about it, times whatever is the size of A. Okay. Right. Because size of A is integer or 4 bytes, it will shift by for every I, that many 4 bytes, it will shift from the starting address. Okay. So this is what the pointer arithmetic does. Okay. When you add I to A, right? Because it knows the data type at compilation time, which is not going to change. It can do this arithmetic. Okay. Now to access the exact data present at the ith location, we dereference it. There is the star operator, okay, on the output of A plus I to say that I'm accessing the ith element of A. What I'm getting at is this syntax and this syntax are exactly the same. Actually, it just so happens that A of I is written to actually return this guy. Okay. Something to remember. Right? Next. Uh, you can use the same thing in printing the value also. So okay, I'm printing the ith value of A. All right. So I'm referencing A with the ith at the ith location. All right. It prints the values from 0 to 9. Okay. Now I do have integer P and integer P pointer and integer A pointer. Right. So what if I do this? What do you guys think will happen? What does this line mean? P equal to A. Remember, P is this guy and A is this guy. And I'm doing P equal to A. Right. A of 0 is a value. Okay. Remember, P is a pointer and A is also a pointer. Think in that direction. right? That's correct. That's a good direction to think towards. Yes, yes, that's correct. First address of A. Yes, that's correct. Yes, these are correct things. Yes. So if you think about it, yeah. So A is actually a collection of an array. Yes, but in itself, A is a pointer. That is correct. And the address of A, whatever it stores, first address is stored in A, right? And when you do P equals to A, you are storing that address in P. Nothing stops you from doing that because it was earlier pointing to I. Now it will just point to A. So you can repeat everything here that we did. Okay. You can actually print from it. It's already written already. So we might as well print it. So here I'm just going to change this to P. Okay. I'm printing A. Notice here. Okay. It just prints it twice. Oh, maybe I'll just uh, little difficult to see. So I'll just comment this so that. Okay. So remember, I did not use A here. Okay, to print this, I used P. Right. So P now because it has the address which is that of A, I can use P itself to iterate through the array. Absolutely fine. Okay. Now because of that, if I increment P, and remember this works because both A and P are integers, like integer data types, like pointers, yes, but more specifically they're integers, integer pointers. Okay. Because of that, if I iterate through the array of 10 values, it prints 0 to 9. Okay. Crucial difference, I do not use A here, I use P. Okay. Clear? Any questions? Okay. What if we do the opposite? What do you guys think is going to happen? Again, nothing has changed. A is integer pointer in a way. P is also a integer pointer. Okay. So A equals to P. Is there any difference between the previous line P equals to A or not? Try. I'll give you guys some time. Think about it. Try to compare between those both these cases where you have a pointer which is pointing to an array A and writing that starting pointer to an another pointer P. But this time you are writing the original pointer, like so the P, to the place of A. Okay. Think what is uh, going to happen. Like, yeah, try. Okay, I'll just give the answer. So this is not allowed. Okay, as you'll see, this error and everything. If you think about it, you have an array, okay, which was being pointed to by A, right? When you overwrite the starting address to with address with whatever P has, where does this array go? There's nothing pointing to it. Okay, so this is not allowed. Okay, implicit assignment like this is not allowed. Okay, that's the reason. Because if you think about it, when it goes out of scope, it'll get destroyed. That's fine. But if you overwrite it this way, so how do you destroy that array then? Okay, so hence this is not allowed. Okay, all right. Let's yeah, take another case. But this time this will be contrast. Okay. Now let's go with main. I have, let's say, integer I, which is 10. Integer pointer, let's say ptr, which is has the address of I. Another integer, this time a reference, which is taken from I. Notice the syntax. So I is a variable, specifically integer, which has the number 10. You have pointer ptr, okay, which has the address of I, okay. So it is pointing to I, where which itself holds 10. Okay. But ref is a reference of I itself. So you can think like ref and I are aliases. Okay. So of the same variable, right? So always remember, these three are three different things, but you can change the value of I with all of these. Okay. So if I type ref as 9, sorry that. Okay. It is equivalent to doing this. Dereferencing the pointer and storing 9 to it. Oh, sorry about that. Yeah, it is not throw an error. Okay. We can print it and see for ourselves also. Okay. Right. Uh, let's go with the that ref means I'm printing through the I changed ref and through that I'm printing it. So I'll just put I here. Okay. So I prints 9. Okay. Well, I actually had 10 because we used the reference to change the value, right? So I now has the value as 10. Okay, right. Next, pointer. I'll be more specific using the pointer dereference. Okay, and then print I. Also, it prints I. Okay, and if you see, the ref actually prints 9 because the value is already changed by a pointer. Okay, because it has changed, even reference also update gives you the correct updated value, which is 9. Okay, right. Now let's assume I have a constant integer pointer, which is, let's say, const ptr, but this time it is pointing to I and n. Okay, and furthermore, I have a const integer reference, which is const underscore ref, which is equal to I. Okay, now what does this mean? As in, you had original values pointer and you had an original value I. Now I can change that value there using the pointer ptr and also using the pointer and the reference ref, right? So the pointer ptr can be used to change the value, okay? Because the state is a pointer pointing to the actual address. Very similarly, the integer reference also can change the value instead of reference to the original I, right? But if you take this example where we are using const pointers and const references, the const pointer will be a const pointer, right? So it cannot actually change the value there. Even const reference, it cannot change the value because it is a const. These variables themselves cannot be used to change the value, right? Okay. So let's say I use const reference as 9. I'm doing exactly the same thing as before. Okay. Let's say we don't change it. It should actually print 9. Uh, sorry, 10 now. Let's check that. Okay. Prints 10 in both cases because they have not been changed. But now let's try to change them using const. Remember what I said just now? Because these are const variables, okay, they cannot change the value by themselves. Okay, because these are const references, right? That's what is also throwing the error as. So this is not allowed. But remember, we were able to change I, right? It just so happens that we used pointers and references which are not const. And remember, the value of I can be changed. Okay, because it is the variable I itself is not const. So the value it holds can be changed. Okay, which we did actually show here, right? But what if you have a const pointer and references and you want to change the value? Okay, so what you can do is temporarily make it not const using const feature. Okay, so what you will do is give the integer reference as the template. Okay, give the variable itself. Okay, and set it to be 9. Yeah, sorry. This is the C++ style of looking at const cast. This is also a sort of a typecasting where it may be a bit of a misnomer. When you use the const cast, you don't actually make it const, like casting to a const. It's more like you're casting a const variable, like something here, to a not const value. Excuse me. Okay. Remember, When you have a reference like this here, which is of const, okay, but whatever variable it is actually pointing to, here in this case I, that is not const, right? You can actually use this um, variable here to change the original value. Okay, you just have to make the variable not const temporarily, and the recipe to do that is to use const casting. Okay, do not get confused. Const casting does not mean you're casting to a const. It's more like temporarily not promoting the variable to be not const. Okay, that way you can think this. Okay, now let's look at the put. It compiles fine. Yeah. Okay, no errors and everything. Now let's print I here, or actually let's do this. Yeah, let's use this print I, but using the const ref. Okay, I mean we did change it to const ref, so just using that. If you see, it prints 9, and we do not change it through these guys. We changed it through the const casting. Okay, clear? So this one is the C++ type of changing your variables. There is a C style. Maybe I'll just rewrite it here. Okay. So what I will do is a reference cast, use the const ref. Okay. And yeah, that's it. Just that's it. And well, yes, this is shorter in syntax. I agree there, but the C++ style is always more explicit in conveying what it is actually doing. So yeah, take your pick. I personally feel this is more clear. Again, performance wise, you don't have to worry. They are doing exactly the same thing. So yeah, choose whichever. Both of them change it to 9. So when I print, it prints 9. Okay. Essentially, what we're saying is I'm temporarily considering const reference here, temporarily as an integer reference. Okay, and writing the value 9. Here also, very much the same way. I'm temporarily considering this const reference as a not const, so that I can change the value you're referring to. Okay. Now, very important. What if the original value was const? What do you guys think will happen?
I think we should not be able to change it at all
Okay, why?
because it was declared as constant during declaration.
Yes, that's correct. So if your original variable, whichever all these pointers, not pointers, references, whatever is pointing to, if the original value has been declared to be const, that means it is out of it is like in untouchable. It can't be changed. Okay. So in that case, even if you try to typecast it all this to um, not const for a temporary basis, it does not matter. The original variable is straightforward, not going to change. You can actually check that. Okay, it will throw errors and everything. You cannot even change these values. Okay, right? Oh, it actually did. But okay, that's a nice thing about const references. Um, it internally uh, checks it if it can change it or not. So it did not change it. It just gave up. Yeah. Hey, and in the C style array, it just also again C does not have this checks to throw that error or anything. You can actually, I think there are member variables of const cast which you can um, call to check if the variable is actually const or not. But anyway, nonetheless, yeah, it just did not change it as you can see, and just yeah, that's it. Okay,
Can you compare it with minus W all? I think it should give a warning or something. No?
W all. Yeah, it should, I guess. I don't know if this G plus plus does. Okay, here it does. Unused variable. Yeah, we did
Didn't
not actually
notice
use it.
it.
Hmm, That's it. We don't use it. That's all. comment is okay. Then yeah, we don't use these variables, which are just normal ones. But other than that, yeah, everything all good. Okay. Yeah, very similarly, we can do the casting, not from just references, but from the pointer also. So, uh, yeah, this guy. So if I dereference it and try to set it to 9, sorry, let's comment all this. Yeah, error. Okay, yeah. So far fine. These are all don't give you an error. But what if we have this line? Essentially the same cost reference, but trying to change the value. Okay, so because this is a pointer, I have to dereference it first and then write the actual value. So here, if you see the error, because this is only read only, or this is a const. So can we do the same prescription of const casting and everything to change this? Yes, we can. So we just write here, comment this for completeness. And yeah, so I'll use the const cast. Okay, it takes integer, sorry, our template as not integer reference, but integer pointer. Okay, and input as the variable itself. Okay, but remember, what does this cast the const integer pointer to? It casts it into integer pointer. Okay, now for this point, you have to dereference it so that you can set the value. Okay, right? This is the C++ style. Okay, and this is the C style. What you do is just integer cast reference. Sorry, this whole thing has integer pointer, then dereference it. Okay, so my bad. Integer pointer. Yeah, you cast it as integer pointer and then dereference it. Okay, so this is the C style. All right. Now printing the same thing. First of all, the const pointer way. Okay. So that prints 9, right? And then the const pointer, but through the C style. So first was C++, the second one is C style, both print 9. Okay. You can actually have all this on, so that should be okay. Yeah. They're all set to the same value anyway, so that's all. Any errors? Oh, all right. I must have found this one. Okay. So both of them print the same value, 9, and they work exactly the same. Okay. All right. So, right. Any questions? Okay. Um, so yeah, this is more or less what I wanted to cover today. So if you guys have any questions, you can stay back or and ask questions. We'll meet next week. So I'll cover more topics on this typecasting, and also we'll move towards a bit more on this contrasting and others. Um, the main thing we'll focus on is actually how you do the same casting that we saw just now with integer and floating point, right? Where you are sort of reinterpreting, right, the same bits in integer and in floating point representation. So we'll more specifically look at reinterpret cast. We'll also look at static cast. Okay. And because while for C, these kinds of cast typecasting is um, the syntax is the same, but the behavior might differ based on the context. In C++, you are more explicit, as in, do you want to interpret, like, do a reinterpret cast or a proper static cast? Okay, so we'll look more into that. Okay. Yeah, see you guys next week. Oh, just one. Every Monday, there is one session, which is from 6 to 8. No, so the thing is the TA session is just once, but the actual course, I think, has more sessions per week. So yeah, this is just the TA session, which is just once per week. Yeah, sure. Thank you. Thank you, everyone. Yeah. I'm glad you guys like it. Thank you.